Okay, this problem says an object of mass 10 kg is released at point A, slides to the bottom of a 30-degree incline, then collides with a horizontal massless spring, compressing it a maximum of 0.75 meters. The spring constant is 500 Newton per meter. So again, look at this. This spring is 50 times weaker than that pogo stick spring. How much does a pogo stick cost? $25. I want to get that spring for $25. If I get young again, I would make a gun out of it or something like that.
But it can only compress 12 centimeters.
Oh no, we'll fix that. Yeah. Man, don't talk dirty, man. That kind of, hey, don't talk stuff like that, okay? You talk like that, we'll stop all jokes. All right. Where were we? Pogo sticks. Anyway, all right. Compressing it a maximum distance of 0.75 meters. The spring has a spring constant 500 Newton per meter. The height of the incline is 2 meters, and the horizontal surface is frictionless. This surface is frictionless. What is the speed of the object at the bottom of the incline? Whoa. Is the entire surface frictionless? What is the speed of the at the bottom? What is the work of friction on the object while on the incline? Oh, okay. So, oh wow. So here's how you have to do this. So, what is the speed of the object at the bottom of the incline? So we'll have to calculate the speed of the at the bottom of the incline from the compression of the spring. This is frictionless. So let's say the faster it's going at the bottom, the more the spring compresses. Okay. Now here's the deal. If in this problem there is friction here, but if this was a frictionless surface, if both of them were frictionless surfaces, this would be a perpetual motion machine. That would fall down, compress the spring, then go back up. Keep doing that for billions of years. Yeah. Now, it so happens that there is friction, so what will happen? It'll come down, compress the spring, and then go back up. But it'll go back up less. And eventually it'll stop. Yeah. All right. And so what happened? This potential energy got converted to heat over here, if that's where it got stuck. Okay. All right. So what is the speed of the object at the bottom of the incline? So, so we'll just draw the horizontal portion, and then it compresses the spring. Okay. So this will be the initial energy, this will be the final energy, and I'm going to start doing stuff fast. So initially you have kinetic energy, that's at the bottom of the hill, and that gets turned into spring potential energy. Okay. You guys understand all of that? I've skipped it. Oh, well, okay. All right, so the spring was compressed 0.75 meters. So here we go, 500 Newton per meter. Okay, so what we have found is, what is this? What did we just find?
On the bottom of
That's right. So you release this from there. This has some friction, but it's not enough friction to prevent it from sliding down. And this gravitational potential energy got converted to, some of it got converted to kinetic energy. And the rest was lost to friction. By friction, it was converted to thermal energy. Okay. So what is the speed at the bottom? What is the work of the friction of the object while it is in the incline? All right, so all right. Again, now we'll use work energy theorem. Net work done is equal to final kinetic energy minus initial kinetic energy. We just found the final kinetic energy. Initial kinetic energy is 0. Okay, so gravity, normal force, and friction force. Those are the three forces acting on it. So the net work done is work done by the friction force, work done by gravity, work done by normal force is equal to final kinetic energy. Okay. Normal force, of course, does 0 work. Work done by friction is what we are trying to find. And work done by gravity is easy to calculate. mgy final minus mgy initial. And that's equal to final kinetic energy. And we'll use this as the reference level. Y final is 0. Okay. So work done by friction force is Ke final minus or minus is plus, and then you bring that to the other side. It's mgy initial. And what is it that you want for the friction work done by the friction force? Is it positive or negative? Friction forces always do negative work. Okay, so what that means is the initial potential energy should be greater than the final kinetic energy that showed up. If it was a frictionless surface, this would be 0, and then all of the potential energy would show up as kinetic energy, and that would be 0. Yeah. All right, so let's put in the numbers. One half 10 times 5.3 square minus 10 times 9.8 times 2. Okay, here I haven't put units because I don't have space there. So minus 55.6 joules. So that's the work done by friction force. Okay. Then the spring recoils and sends the object back towards the incline. What is the speed of the object when it reaches the base of the incline? Very good. Everybody understand that? Because that surface is a frictionless surface, and so I won't even bother solving it. If you guys have any question, go to him. And what's your name, my friend? Kendall. Okay, Kendall will help you out. Okay, so what Kendall is saying is this potential energy will get converted back to that kinetic energy. Okay. All right. What vertical distance does it move back up the incline? Okay. Now this is this is a bit of a problem. Okay. We have to find mu first. Okay, so we calculated where is the work done by friction force? Whoa.
Horizontal friction.
What happened?
There's the friction.
Oh, I just ended up adding a page. Okay, I'll have to move this over. Okay. I added a page in the wrong place, but we'll fix that. Kendall threw me off. All right, 30 degrees, 2 meters. So we'll have to do a little math. 30 degrees, 2 meters. D is 2 meters by sine 30. Again, just like last time. Okay. Four meters. D is 4 meters. Okay. And the work done by friction force. Work done by friction force is minus FD equal to minus 55.6 joules. Okay, so the friction force was equal to 55.6 joules divided by 4 meters, and that is equal to 13.9 newtons. Okay, so the friction force is mu k times the normal force, and this is just mu k times the normal force is equal to mg cosine theta. All right, so now here's the little trick that you have to notice. When the block is sliding up the incline, the friction force is the same, nothing changes. The friction coefficient doesn't change, except that the friction force is in the opposite direction. Okay. So now let's get the object going up. Let's add a page below. All right, so we got the block going at 5.3 meters per second. It's come to rest at that distance, d final. Okay, and the work done by gravity plus work done by friction force should equal my final kinetic energy minus initial kinetic energy. We know the initial kinetic energy, final kinetic energy is 0. Work done by gravity is minus ug final minus ug initial. Y initial is 0. Y final is what we are trying to find. So this is 0. Work done by the friction force is d final. So this is quite a problem. If you make sure you understand this, you will. The rest of them will be a piece of cake. Fk d final. This d final is y final divided by sine 30. Okay. All right, we'll drop all the minus signs. Okay. So y final is mv initial square divided by 2 times mg plus, I've taken y final common there, and these are the two terms, mg plus, I hope you guys understand this, fk by sine 30. Yeah. And sine 30 is a half, so that becomes okay. Sine 30 is a half. All right, so now we can put in the numbers. The block is 10 kgs, 5.3 meters per second square. 2 divided by 10 kg into 9.8 meters per second square, plus 2 times the friction force, and the magnitude of the friction force was 13.9 newtons. Okay. And so this will tell you how far it will rise up. .12 meters. So again, this thing slides down from 2 meters, and after its collision back, it comes back half the distance, roughly half the distance. Okay. All right, guys. I will see some of you guys in lab.